Okay, let me welcome all of you back to another session of organic chemistry. In today's session, we are going to conclude our discussion on chapter 22. And before we start the session today, just a couple of announcements. I want to remind you that the online review session is scheduled for tomorrow, that is Friday, April 4 at 8 p.m. We are going to review for the for exam number 3 that is scheduled for Tuesday, April 8. Okay, also want to remind you that the homework assignment for chapter 22 is due on Sunday, April 6 at 11 p.m. Okay, so what we want to do now, we want to finish up our discussion on chapter 22. But before we do that, let us go over the quiz question that you guys have just taken. Okay, Akira, can you go ahead and read this for us? Okay, thank you. Okay, for this problem here, you are supposed to provide the missing reagents for the following sequence of reactions. So this is just a case of knowing your reagents at this point. Okay, so what we have here, we are going from this molecule here. And then we need to do an alkylation. In other words, we are forming a new carbon-carbon bond right here. So what reagent do we need for this? Anybody has an idea? What do we need to do here? What is the first thing you need to do? Form the enolate. Okay. What are you going to form the enolate with? LDA. Very good. Okay, so the first thing we do, to form the enolate using lithium diisopropylamine, LDA. And once we form the enolate we are going to form will be on this carbon here, abstracting this hydrogen here, because the pH, the pKa value for this hydrogen is about 11, whereas the pKa value for this hydrogen here is about 20. So therefore, this hydrogen here is at about 10 to the power of 9 more acidic than this hydrogen here. So therefore, the LDA will simply come here, abstract this hydrogen here to form the enolate, because it's a lot more acidic than this one here. Okay. So now once you form the enolate, then what do you do? Step 2 would be, okay, alkylation. In this case, you are going to use methyl. You could use methyl bromide, or methyl iodide, or methyl chloride. Okay, and that is your alkylation right here. Okay, very good. Okay, now, step B, we want to go from here to here. At this point, what are we doing? Essentially, what we are going to do, we are going to lose this here. In essence, we are going to do some decarboxylation. And so, therefore, to do decarboxylation, what do you need to do first? Okay, you need to transform the ester. This is an ester, right? You need to transform the ester to a carboxylic acid. And to do that, you do acid catalyzed hydrolysis, okay, or Fischer esterification. Yes, you have a question? Oh, okay, I see. Okay, the question is, instead of using LDA, can we use a very good question, can we use hydroxide? Okay, no, we cannot use hydroxide here. I'll tell you why. Look at this here. We have an ester here. If you have an ester, and you have hydroxide, of course, the hydroxide is in the presence of water. What you are going to get will be this here. You will get basic hydrolysis of the ester to the carboxylate. Okay, so that is what you are going to get. Okay, plus of course you get, in this case. Okay, so you will destroy the ester functionality if you use the hydroxide. Okay, and that is why we do not want to use hydroxide as a base. Okay, in the case of LD, okay, we say that we have to do the carboxylation, and to do the carboxylation, you need to transform the ester to carboxylic acid. So therefore, what is the first step you need to do here? Hydrolysis, right? Okay, so step 1, you do the acidic hydrolysis, and then step 2, you apply heat, okay, and that will do your decarboxylation right here. So therefore, you have this product here. Okay. Next step, we are going from here, this compound here to here. At this point, we want to form a new carbon-carbon bond, another alkylation. So what do we need to do here? LDA, very good. Step 1. Now, why do you want to use LDA and not hydroxide? Because the LDA will selectively deprotonate this hydrogen here, because it's more bulky than any other than the hydroxide, for example. Okay, because of steric hindrance. So instead of the LDA coming here to remove this hydrogen here, okay, it will simply come here to remove this hydrogen here. Okay, and then once you form the enolate on this carbon here, then you add the alkylating agent, and then you are going to form your new carbon-carbon bond. Okay. Okay, so let us go to the next one. Okay, Chad, can you read this for us? Okay, thank you. Okay, so in this case, we will need to do a synthetic design. Okay, so starting from malonic ester and other appropriate reactions, write a synthetic scheme for cyclopentane carbonitride. So the first thing, you need to know what this cyclopentane carbonitride is. You also need to know what malonic ester is. Okay? So in essence, they are asking us to do this. Take ethyl malonate or malonic ester, and then you form this compound here, cyclopentane carbonitride. So you have a 5-member ring attached to a carbon-nitrogen triple bond. Okay. So that is your cyclopentane carbonitride. So therefore, what do we need to do here? Let us do some analysis. You want to start off by saying this carbon here, right? Well, we want to start off by saying this here, this carbon here. Let us start with this carbon here. this carbon here will have to be, okay, I lost my CH2. Okay. We start by assuming that this carbon here has got to be one of these carbonyl here from the malonic ester. That will be your first assumption. And if that is the case, then you then make another assumption that this here, this carbon alpha to the carbon nitrogen triple bond will have to be this alpha hydrogen, this alpha carbon here, alpha to this carbonyl right here. Okay, so if you make that assumption, okay, that simply tells you that what you need to do here, you need to form two bonds. You need to form a bond between this alpha carbon here, right here, one bond, another bond here, right? So you need to form two bonds, and both of those will have to be intramolecular alkylation, because you are forming a ring. Okay? Okay, so let us see, how do we approach this? So how do we approach it? What is the first thing we need to do? First thing you do? From the enolate, okay. What base do you want to use for the enolate? Ethoxide, very good, because you have ethoxide in here, okay. So if there is any trans esterification, you will be getting the same ester, okay. Okay, so you take the ethoxide. Okay, so we are going to form this. And then we have this. So from the enolate of the ethyl malonate, and then what do you do after that? Add a, okay, we want to use a so you need how many carbons here? 1, 2, 3, 4. You need 4 carbons, because this is the alpha carbon coming from the malonate. Therefore, you need 4 carbons. So let us see. 1, 2, 3, 4. So when you see this situation here in which your alpha carbon is part of a ring system, then you know that you have to do an intramolecular SN2 reaction. Okay? Okay, so the first thing that happens, of course, do your SN2 reaction. So we form our first product, in which we now, let me change the color of this. Let me use blue color here. I say this is blue. Okay. So now we have this. And then you have this. This is 1, 2, 3, 4. 4 carbons, okay? And then what is the next step? Another enolate formation, right? Very good. Using ethoxide, okay, so and that will remove this proton here, form another enolate on this carbon. Okay, and now once you form this enolate, now you're now going to get your intramolecular SN2 reaction, in which this simply comes here, displays this. Of course, you don't have to give this mechanism unless I ask you for the mechanism. Okay. Okay. So now, what do you get? You get this. And this is this carbon right here. Okay, so now we have this, and now we have this. We have that. So now at this point, what do we want to do? We do hydrolysis. We want to hydrolyze the ester to carboxylic acid. So you form the diester. And once you form the diester, now we apply heat. And now we are going to lose carbon dioxide. And this hydrogen here, all this hydrogen will now come to this carbon here, to this alpha carbon here. So now we have this. Okay, we form that. Now this is where we are. This is what we wanted to make. So now what do we do from here? Now that we finished the malonic ester synthesis. So what do we do now? Carbon dioxide is given out here. What do we do next? We want to go to the nitrite. What do you do? Okay, use ammonia. NaO. Oh, you want to make it into alcohol? No. You want to do the acid chloride? Okay, well, you could do that. Okay. Want to do acid chloride? Okay, so now we form this. Okay, then Na3. Okay, we want to form the amide at this point. Okay. Very good. Then thionyl chloride. Okay, very good. Then thionyl chloride will react with the primary amide to give you the nitrite. Okay. Okay. Yes.
Why couldn't you form the alcohol and dehydrate it, and then you could clean?
Turn this to alcohol.
Which one?
No, if you turn this to alcohol, okay, then what do you want to do?
Dehydrate it and clean it.
Turn it to alcohol, then dehydrate, okay, to form a alkene.
Then you can cleave it to form a ketone, form a secondary alcohol.
Okay, but where do you get the extra carbon?
Okay. When you get the secondary alcohol from the...
You get the alcohol from here?
From where?
You said this...
After you form the alkene and then you cleave it...
But how do you form the alkene though?
Dehydrate it.
Dehydrate what?
The cyclopentane with the CH.
No, that will not work. That will not work. Okay. So another way in which you could also make the the amide, you could make the amide directly. If you take this here, carboxylic acid, you could go directly to the amide by reacting with ammonia in the presence of DCC. DCC in the presence of ammonia. That will take the carboxylic acid to the primary amide, and then from the primary amide you then do the dehydration to get the nitrile. Okay. Okay, so let us go to the third question here. Okay, Camille, can you read this for us? Okay, thank you. Okay, so in this case, we are asking you, starting from cyclohexanone, ethyl malonate, and other appropriate reactions and reagents, provide a synthetic scheme for this compound here. Okay, this here will require that you do a lot of thinking. Okay, this is more than just knowing your reagents. Okay, so this is where you need to begin to think critically. Okay, so let us take a look at, let's do the analysis here. Okay, you want to start with ethyl malonate. So the first thing I will do is that, of course, you know you have the carbonyl right here. Therefore, this carbon here must be the alpha carbon from the ethyl malonate, right? So you make that assumption. So if that is the alpha carbon from the ethyl malonate, so what that tells you is that you have to make a new carbon-carbon bond between this carbon here and that alpha carbon. Okay? Okay, so once you know that, okay, keep in mind this is what we want to do here. We want to go from here, starting from cyclohexanone, to this here. Okay? So for you to make a new carbon-carbon bond between the alpha carbon and this carbon, what this is also telling us, we also need to make a new carbon-carbon bond between this carbon here and another carbon. Right? Okay? So then the first question that should come to your mind is, how do we go from a ketone? How do we add a carbon to a ketone? Wittig, exactly. You could use a Wittig. Okay, so let us start. You could use Wittig. So you need to know your reagent first, then you need to know how to use it. Okay, so I say I want to use a Wittig. Okay, I use that that Wittig, and that will give me this. Now, once you get that alkene, then what do you do with it? What do you want to do? You want to add antimicrobial addition of water? Okay. Okay. You know the reagent for that, borane, followed by hydrogen peroxide in basic medium. And that gives us this. Now, what do you do with that now? You want to add, turn the alcohol into bromide? Okay, very good. And then you know the reagent for that. Okay, now that you've done that, now what do we do now? The malonate, okay? So now we take our malonate, okay, with etoxide, right? Okay, take the malonate with etoxide. Of course, what would the etoxide do? Form the enolate ion, and then the enolate ion will now react with this alkylating agent here in an SN2 reaction. This is a primary carbon right here. Okay, so now we have this. Of course, we still have one hydrogen here. Okay, now what do we do after this? Hydrolyze, okay. Okay, so that becomes, let's change the color here, so. Okay, then you apply heat, and that becomes this here. Wait a minute, I'm missing a carbon here. Sorry about that. Okay, and then once you apply heat, you get your product. Okay, plus carbon dioxide. Okay, so in this particular problem here, this does require that, of course, you know your reagents, and then you simply know how to use those reagents. So this is where you really have to think critically. Okay. Is there any question on this before we move on? Yes, yes, it's going to release carbon dioxide. Okay. Okay, now let us finish up on chapter, a few more items on chapter 22, and then after we do that, I do want us to also do some problems before we leave today. Okay. Going back to chapter 22. Okay, what I want to discuss today, a couple of reactions that we have not done before, which are also related to the chemistry of enolate anions. We call this the Favorskii reaction. This reaction, what it does is to give us ring contraction Now, if you recall, we told you that you could take this here, to take a ketone, take hydroxide, the presence of bromine, for example, you could get this. to get alpha bromination. You could also do the same reaction with an acid catalyst, hydrogen bromide supplying the proton and the presence of bromine. Or you could use acetic acid as a source of proton, of course in the presence of bromine. Each one of these, this will give you alpha bromo ketone. This will also give you the same product. Okay. Now, what do you do with this? Now, if I now take the Favorskii reaction, if I now take this alpha bromo ketone and I take hydroxide, the hydroxide will form an enolate anion on this carbon here. In other words, one of those hydrogen will be removed. So you now have one hydrogen here. Okay, once you form this enolate anion here, guess what is going to happen? Guess what will happen? We are going to get an intramolecular SN2 reaction. This enolate here simply comes here, attack this carbon here, kicking this out. And then you form this intermediate. This three-member ring intermediate is very strained. In other words, it is very reactive. Okay, so now another molecule of etoxide comes here. Now I'm going to do the nucleophilic addition to carbonyl. Form another intermediate. Let me get this out of here. And what do we get? And then this intermediate is very reactive and it wants to regenerate the carbonyl functional group. So what do we have? We have this here. We are going to reform the carbon-oxygen double bond. Okay, once we do that, instead of the hydroxide leaving, one of these bonds will break. From that enolate ion. Okay? So now what do we have? We now have this. of that enolate ion. Okay. Now, this enolate ion is a strong base, so what does it do? It simply come here to grab this proton here, and electron goes to oxygen, and then we end up with this here. Okay, and then finally, the second step of the this ring contraction. Notice what we've done here. We've gone from a 6-member ring to a 5-member ring, and in the process we have formed a carboxylate. So now all we need to do now is simply now just add acid, dilute acid to this. Sorry. H2O. Okay, so this comes here to pick up the proton from what? The dilute acid. And then you end up with okay, so what does it give us? In essence, you could simply do this. So anytime you have a cyclic molecule, a cyclic ketone that has, say for example, you have this, let's say we have 7-member ring. As long as you have a leaving group in the alpha position, and then you simply say step 1, hydroxide, and step 2, dilute acid. What will be the product? In this case, you are going to go from a 6-member ring to, a 7-member ring molecule to a 6-member ring molecule. And in the process, you are going to form a carboxylic acid. So that is another way of making carboxylic acid. So as you can see here, this is what we refer to as a Favorskii reaction, this particular reaction here. And that is why we say it gives you ring contraction. Okay? So if I have, finish with this. Okay? So therefore, if I have a 5-member ring, say we have a leaving group here, alpha iodocyclopentanone, and then I simply have step 1, hydroxide, and then step 2, what will be the product? Cyclobutane carboxylic acid. Very good. Now, if I ask you for the mechanism, then you give the mechanism. But if you are not asked for the mechanism, just simply give the product. So this is a very good way of making carboxylic acid. Now, supposing you want to do a ring expansion. Okay, we've given you, right now you know only one reaction, one set of reactions that will give you ring contraction. Supposing you want to do a ring expansion. Say for example, I say how will you go from here to here. See, when you guys finish your BS in organic chemistry and you go to graduate school, this is what you do. you design new reagents, okay? So that the undergraduate students have more problem to deal with, right? Okay, this is what we do. We look for new reagents. So now, how do you go from this 5-member ring to 6-member ring? The way to do that, you finish? Okay. Let us say ring expansion reaction using diazomethane. Diazomethane is this molecule here. That is diazomethane. If you take diazomethane, say for example, we take our cyclopentanone or any cyclic ketone, this will react as a nucleophile. You have a nucleophilic addition to carbon-oxygen double bond, right? Okay, so we have this. Let's change the color of the pen. What happens here? This here comes here, nucleophilic addition, because this pi electron comes to oxygen, and then we have this intermediate. Okay, now what is going to happen? What's going to happen? We are going to reform the carbonyl, right? Okay, so we want to reform the carbonyl. When we want to reform the carbonyl, okay, of course we know carbon can only have 4 bonds, so one of these bonds will break, and when it breaks, comes in here, attack that carbon, and the reason why that is possible because this part of the molecule here, this is nitrogen, and you know nitrogen is a very stable molecule, so nitrogen will just be spit out of this here, kicked out of the molecule, and then you have your ring expansion. You see how innovative organic chemists are? Don't you guys want to become organic chemists? You don't want to become organic chemists, okay? No, guess what? If you get your PhD in organic chemistry, you get, right away, you get at least $100,000. And when you go to graduate school in organic chemistry, we pay you to go to graduate school. On the other hand, when you go to medical school, you pay them to go to medical school. So by the time you finish medical school, you are owing about $1 million, right? But by the time you finish your organic chemistry, you'll be making money.
Why they pay
Okay. Okay, so now you have this. And of course, one of these carbon here, this here becomes, that is this here, this green here, okay, plus nitrogen, okay? So therefore, it is possible to expand your ring if you start with a cyclic ketone. It is also possible to contract your ring using Favorskii reaction, yes. This here? This? No, what I'm simply trying to point out that this carbon here is this here. Let me see. This here is this right here. Okay? Okay. Of course, before we finish this chapter, you guys know about the Favorskii reaction that is also related to enolate ion formation. In this case, if you take any carboxylic acid, as long as you have alpha hydrogen, and you take phosphorus tribromide, the first thing that happens, you are going to form the acid halide. In this case, the acid bromide. And somehow, this molecule here form an enol. Okay, this is your enol, acid bromide enol, and of course, you know the enol is always with enol. It is possible to reform the carbonyl and form a transient enolate. Of course, you don't need to write this mechanism unless we ask you to do that. Yeah, somewhere. And then, of course, once you have bromine in the system, before the enolate will pick up the proton here, you simply displace the bromine. Now you get. And that is why when you do this reaction, you add the phosphorus tribromide and the bromine at the same time. Okay. And then finally, once you add water to this, or dilute acid, you hydrolyze the acid bromide to carboxylic acid. Okay? So the way you write this, you don't need to write the mechanism unless we ask you for the mechanism. You could simply do this. You got it? Okay. Okay. You could simply keep in mind. Oh, you want me to go back? Oh, okay, sorry. Yes. Oh no, okay. What is happening this here? Okay. This electron go here. Generally, when you have a carbonyl, okay, could rearrange. It's always in equilibrium with the enol. This is what we call the enol, which is a vinyl alcohol. Okay, so this electron goes here. Okay, and in so doing, this hydrogen here will be pulled off to attach itself to this oxygen. So that equilibrium is always there anytime you have a carbonyl compound. Okay, okay, so therefore you form your enol. There is always going to be some kind of equilibrium between the carbonyl compound and the enol. Okay, so what do you normally do? Say we have this carboxylic acid here. Keep in mind, as long as you have a carboxylic acid with alpha hydrogen, this reaction will occur. We have alpha hydrogen here. So what you do is just say step 1, phosphorus tribromide, and you add it together at the same time with bromine. So phosphorus tribromide and bromine will be added at the same time. And then the second step is the hydrolysis to form the carboxylic acid, either with water or with dilute acid. And that will give you okay. Keep in mind, without the water, what you form is the acid bromide, plus the alpha hydrogen is also replaced by bromine. Okay. If you just do this, this is what you get. Okay, at this point you simply now take water to hydrolyze this to carboxylic acid. Okay, and finally, before we leave this chapter and then do some problem, this reaction you've seen before, the iodoform reaction. Are you finished on this page? Okay. What we call the iodoform reaction. These reactions, actually we use this reaction to determine whether we have a methyl ketone. It happens almost within a few seconds. If you take any compound that has what we call a methyl ketone, any compound that has this kind of functional group right here, a carbonyl of a ketone, keep in mind a carbonyl of a ketone, and methyl group attached to it. Okay, if you take any compound of that nature, and you take hydroxide in the presence of, in this case, let us use iodine. Step 1, and then step 2, you add dilute acid. This is what you get. Plus iodoform. It's a yellow color. And if you take this reagent here, and you take any molecule that has a methyl ketone, within a second you get very solid yellow precipitate of, in this case, iodoform. But you could also do this with a bromine or chlorine. Okay? You take this compound here, as long as you have a methyl ketone. Take this. In the presence of chlorine, for example, we could do that. Okay, of course, the first thing you get is this here. You get the carboxylate, and then once you add the dilute acid, that is how you get your carboxylic acid. Okay? So anyway, it's a very useful reaction. It allows us to go to take a methyl ketone and then form carboxylic acid. Do you want to see the mechanism of this reaction? Okay. Well, no. Okay. Let's go to problem. Okay. Okay. I know that's what you want to know. Is it going to be on the test? Why don't you just know it just for the sake of knowing it? Just for the sake of knowledge, right? Okay. I'll tell you, it does go through the formation of enolate ion. Okay. Let's see here. Jasmine, can you read this first?
Starting from 1,4-dibromo-butane and malonate and other complete reagents provide image for cyclopentol cyclopentol.
Okay, thank you. Let me take this out of here so that we'll save some. Okay. Thank you. So starting from 1,4-dibromobutane, ethyl malonate, and other appropriate reagents provide synthetic scheme for cyclopentyl methyl ketone. In other words, they wanted to make this compound here. I think we did this already. Cyclopentyl. Yeah, I think we did this. Didn't we do this? Or we did not? Okay, anyway. And this time you want to start with ethyl malonate and 1,4-dibromobutane. Okay. Okay, so how do we do that? Some of you will say, well, how do you go from ethyl malonic ester, since malonic ester is supposed to give you carboxylic acid, how do you end up getting a ketone? Some of you will ask that question. So do you have an answer to that? You transform the ester to methyl ketone. Okay, very good. Okay, so let us start. Okay, so we say step 1. Okay, so let us save ourselves some time here. Step 2. Okay, so we get this. One, 2, 3, 4. And then you do another step 1 and step 2. And the reason you know you need to do this, of course, they've given you this starting material to use. And of course, you also assume here, keep reminding you, when you have this kind of problem, you look at the carbonyl, where the carbonyl or the original carbonyl was. Say, okay, if this was the original carbonyl from the ethyl malonate, one of these here, then this must be the alpha carbon, which is this here. So which means that you need to form 2 carbon-carbon bonds to that alpha carbon, and that is using this here. Okay. Okay, so do that. Now we are going to get this. Okay, because once you have the ethoxide here, you abstract this hydrogen here or this proton here to form the enolate, and once you form the enolate, that enolate will simply come here, attack this carbon here in an SN2 reaction, and the bromine will leave, and therefore you form this product. Okay, so at this point, then what do we do? Hydrolysis, sorry about that. And that will give us the dicarboxylic acid. And once you apply heat, okay, you lose one of these as carbon dioxide, and this hydrogen will come to this alpha carbon here. And that hydrogen is now here. Okay. So at this point, then how do we get to here? This is where we want to go. What do you want to do? You want to do an acid chloride and then do a Gilman. Okay. See, organic chemistry forces you to think, okay, to think critically. So when you become medical doctors, you will not be making any mistakes, right? So that you give all the credit to organic chemistry. Say, the reason I'm so good right now is because I did organic chemistry. Okay, so now what do you do once you form your acid chloride? Gilman, right? Very good. So do not forget all of these reagents, okay? I keep telling you those reagents are the ABC, and the right is here, so you know. ABC of organic chemistry. Okay, without them you cannot do anything. Yes.
We can have that facial verification.
This here?
Never mind.
Yeah, that we did that. Okay. Okay. How much time do we have? Okay, we've got 4 more minutes. That's an eternity. If you play football, that's a long time.
Oh, yeah.
Yeah, right? The same thing in organic chemistry. Okay, so now you use the Gilman reagent to give you the product, which is this here. Okay, do you want to do one more?
Yes.
Okay, let's do one more. For you, okay. Let's do one more. Okay. Okay, let's see here. Okay, Ashok, can you read it for us? Oh, you can see it too well, okay. Alexi, can you read it for us? Oh, okay. Erin.
Using acetoacetic ester synthesis followed by iodoform reaction and other appropriate reactions, provide a synthetic key for the following two.
Okay, thank you. Okay, so now another synthetic scheme. Okay, let's do some analysis, right? They want us to start with acetoacetic ester. We know what that's ethyl acetoacetate. That's another name for that. Okay, ethyl acetoacetic ester or ethyl acetoacetate. That is the other name for it. Now, which is this molecule here? You all know this already. Okay, so they want us to start with this. And then they also want you to use iodoform reaction to make this here. Okay, so what is the first assumption we need to make? We take a look at this ester here. We say this carbonyl here. We assume that this carbonyl must be the carbonyl from here, because keep in mind this is in the acetoacetic ester synthesis, you form a ketone, so it must be this here. You got to make that assumption. Acetoacetic ester gives you the ketone, not the carboxylic acid. So you assume, okay, this must be this here, this carbon here. If that is the case, then you have to say that this here, this carbon here, must be this carbon. Okay? Because we have to lose this. Okay? So far so good, right? Now, then we have to also say that this carbon here must be this carbon, because the rest of this molecule here is still here. Okay? So this carbon here must be this carbon. You follow me so far? Okay. Therefore, what do we need to do? What that tells me is that we need to join this carbon to this here in acetoacetic ester. Okay, which will be joining this and this. Okay? Okay, if that is the case, how do we join them? We have an alcohol. So what do we do with this? Convert to a good leaving group, like a bromide, right? Okay, you guys know that already. So, you finish your analysis. Then we say, let's take this phosphorus tribromide, right? Okay, let's call all of this here, to save ourselves some time, let's call this R. Okay? Let's make that R. You could do the same, just let me know what your R is. Okay, so therefore we say we have R, CH2, bromine. So we have converted this alcohol to the bromide. Now then, what do we need to do now? We now take our acetoacetic ester or ethyl acetoacetate, in the presence of ethoxide, and what does that do? It forms the enolate, right? And once you form this enolate here, attack this carbon here, right? So therefore we form this product. And I'm sorry, yeah, that's right. And then this R here is now here. Okay? Well, now once you form that, then what do we do at this point? What do we do next? Because we want to lose this, right? Hydrolyze. So that becomes and this is here. Okay, now once you apply heat, we are going to lose this carbon dioxide, and this hydrogen will simply come here. So now we form this. Now CH2 and our R right here. So we now form that ketone. Okay. Now once we form that ketone, then what do we do next? We do iodoform. Iodoform reaction in the presence, hydroxide in the presence of iodine, step 1, and then step 2, we add dilute acid. Okay? And then what does that give us? What does that give us? The carboxylic. What the iodoform will do is to turn this here to carboxylic acid. This will be lost. Metal will be lost. So this becomes carboxylic acid. Okay? And then we have this. And our R is still here. And then what do you do to go to here? Yes, now you do the Fischer esterification, okay, using ethanol, because you have to make an ester. Okay, so now we do Fischer esterification. In the presence of, say, sulfuric acid, some strong acid, you now form your ester. So we have gone from this here. Keep in mind this is our R at this point. Wait a minute. I'm sorry, that's not what that's not where we're going. To give you the final product is supposed to be this one here. Actually, I should just have this. Let me do this better than that. Take this out of here. Okay, we want to go to here. Okay, so we take ethanol, presence of sulfuric acid, and that is your Fischer esterification. Okay, folks, so I know I've taken a little bit of your time, and I want to thank you for having the patience today. So anyway, tomorrow, I will see you tomorrow online. I will send you a reminder for that session. That is at 8 p.m. tomorrow. Okay, so enjoy the rest of your evening. Yes. Go back. Oh, no, keep on going. Oh, let's see here. Let me know when I get there. Okay. Oh, folks, I do have your quiz number 8 here. Let me give that back to you.